We talked that the short key of this was its downfall, so it was time to move on to a more secure cipher. For this reason, actually, NIST organized a competition, and the winner was AES. And currently, as for arguably the most used encryption algorithm is AES. So before seeing what AES is, let's recall what a substitution permutation network was. So I want to remind you this because AES is a substitution permutation network. So recall that a round of an SPN cipher consists of 3 layers: key addition, where you combine your key material with the plain text; substitution, and this layer provides confusion; and permutation layer, which provides diffusion. So AES and present are examples of SPN. AES is standard for block cipher by ISO and NIST. Present is a lightweight cryptographic standard standardized by ISO. So a picture would be something like this. For an SPN cipher, you have the plain text block here and your secret key here. The key schedule algorithm provides round keys. So you combine your round key with your plain text block initially. This is sometimes referred to as initial whitening. Generally, we prefer to use XOR operation here. So we add bits to bits. The single round consists of substitution, permutation, and add round key layers. So if you repeat it many times, you obtain the ciphertext block at the end. So let's see how AES works in this case. Advanced Encryption Standard, shortened as AES, was the winner of the competition, Advanced Encryption competition, which was organized by NIST. This cipher, actually it was called Randall. It was designed by John Damon and Vincent Raymond. And so the name of the algorithm actually comes from the names of the designers. But since they won the competition, now it is referred to as Advanced Encryption Standard. It was standardized in 2001. Other finalists of the competition were Serpent, Twofish, RC6, and Mars. So you can see these algorithms in some of the open source libraries like OpenSSL, but they're not standardized anywhere. So, I mean, as far as we know that they are secure, but using them might not be a good idea since they're not standardized anyway. So AES has block size 128 bits and key lengths. It supports 3 key lengths: 128, 192, and 256 bits. Actually, this was one of the requirements of the competition. So depending on the key length you choose, the number of rounds changes. For a small key, you use small number of rounds, and for the largest key, you use 14 rounds. So this might be counterintuitive. Some students sometimes think that choosing the larger key actually would require you to use less rounds, but you have to look at the picture in a information theoretical sense, because here you are trying to combine the plain text information, which is the block size is fixed, with this many information. So in order to provide better confusion and diffusion, it is meaningful to have more rounds here. So there are many attacks. The literature is full of them, but known attacks are ineffective. So we keep using this algorithm all the time. Let's see how it is defined. We said that the block of AES is 128 bits. So it is divided into 4 words of 4 bytes. Each word can be seen as a row. So you can represent it like this by a 4x4 matrix. So each box, actually, each rectangle represents a single byte of the plain text block. And we perform operations on these rows and columns. Round function of AES is designed as follows: key addition, sub-bytes, shift rows, and mixed columns. So as you can guess, key addition is XOR with the key. So this is the key addition layer. In the sub-bytes layer, we use S-boxes, so this is where the confusion layer comes from. And shift rows and mix columns, actually, both of them represents the diffusion layer. You might think that why there are two different operations. We will see that shift rows is just rotation to left. So we are rotating rows to the left. But if you only do this, there wouldn't be any operation that works on the columns. For this reason, we have a matrix multiplication which multiplies columns with a matrix. So this way, we try to achieve the best diffusion. When you perform decryption, you have to perform the inverse operation here. XORing something has no inverse since it is just in modulo 2. So in decryption, key addition is again the XOR with the round key. In the sub-bytes, you use the inverse of the S-box. In the shift rows, instead of rotating left, now you are rotating right. And at the mix column, instead of multiplying with the matrix M, you are multiplying with the inverse of the matrix. And before seeing the operations, let's see how the key schedule works. This image is taken from the book, The Block Cipher Companion by Lars Knudsen and Matthew Robshaw. So 128-bit key, if you choose that key length, is represented with 4 words of 32 bits. So these 32 bits actually here rotated 1 byte to the right, then S-box operation is applied. A round constant added to this byte, then this is XOR to the leftmost word, and it is XOR to the next, and next. So this is the key schedule for the case when the key length is 128. The picture is somewhat similar when you choose other key sizes, but when you choose the larger key size, the operations, there are more operations. For instance, when the K is 256, you will see there will be more S-box operations for the rightmost part and so on. But this is the one that we use most actually. So you can think about it, this picture in your mind when we are talking. So let's look at the steps with this picture. We said that first step is add round key. So your key is also round key is 128 bits. So you XOR actually whole 128-bit block with the 128-bit round key. But in the picture, you can see that you might think it is if we are XORing the bytes themselves and write to the correct place. Next step is sub-bytes. So each byte is taken and fed to the S-box, and the result is written to the same place where you take the input. So this S-box is a special S-box. It is defined like this. So if your input, for instance, 3B in hexadecimal notation, so since this is an 8x8 S-box, the input can have 256 values and 256 output values. So for example, if the input is 3 bits, in this table, you look at the third row and bit column, you realize that the output will be E2. So you replace your input 3B with E2 and write it to the corresponding byte place. So when you need the inverse S-box, you have to change this table into the inverse of it. This S-box is special because it is chosen as the inversion of the input byte X when viewed as an element of the Galois field 2 to the 8. This provides optimal resistance against linear and differential cryptanalysis. So there's an open question about this. So question is, can you find a better S-box, 8x8 S-box, which provides better resistance against linear and differential cryptanalysis? And this problem is still open, and we don't know if there is such an S-box, and we cannot check all of the 8x8 S-boxes because the space is really huge. Our computational power is not enough to check all of them. So let's look at the shift rows operation. First row, there is no change. You just take the first row and write it here. In the second row, or if you start counting from 0, so 0th row has no change. First row has 1 byte shift to the left. Actually, this is not a shift but a rotation, because you take this byte and move it to left, and the leftmost byte is taken here. So as you can see, it is written like this. In the second row, you shifted 2 bytes to the left, and in the third one, you shifted 3 bytes to the left, and obtain this one. So as you can see, this provides a diffusion among rows. Now we need to have a diffusion in the column. So this is performed by mixed column operation. You have the matrix, and you multiply the matrix with every column. So if it is this column, you multiply this matrix with this column and write the result here. So actually, you repeat this process 4 times. So this is how the steps of the AES works. This matrix is also carefully chosen. It is derived from the parity check matrix of a maximally distance separable code. These MDS codes are used in coding theory a lot, but they are beyond the scope of this lecture. But M's feature about branch numbers is important for us, because this actually provides security against differential cryptanalysis. So it is also an active research area about MDS matrices for AES. So people are trying to find similar MDS matrices, but have better security against some of the non-cryptanalysis techniques. So you can see a lot of papers about this topic. So finally, let's talk about performance of AES. Efficient AES implementations are successful provided on many software and hardware platforms. You can see very good optimizations almost to every environment. I think you can even have hardware implementations as low as 2,400 gate equivalents and so on. But still, lightweight block ciphers are necessary for constrained devices. This is why NIST is currently having a lightweight crypto standardization competition, and probably it will be continuing for 3 or 4 years. But at the end, NIST will have another standard for encryption, and it will be a lightweight algorithm. But NIST's approach is like this: if you can use AES in any place, just use it. If it is enough for you, just use it. But if it is not sufficient for you due to maybe the performance or the requirements that is not valid for your environment, then it is better if you use the lightweight standard that is going to be chosen in the following years. And special case for AES, there is a special case we need to talk about AES, because modern CPUs, I think since 2010, Intel and AMD CPUs come with hardware level instruction sets. This is called as AES-NI instructions, so generally shortened as AES-NI. So instead of writing a software code, you can use these hardware instructions in your, for instance, C implementations to use the hardware level implementation of AES, and it provides around 10 times faster results. So you cannot write a software level implementation that can beat this hardware encryption. An idea for this approach was as follows: USA made it a must for state officials to keep their hard drives always encrypted. So when a laptop is stolen or lost, documents cannot leak because they're already encrypted. But full disk encryption results in a 20 to 40% performance loss, depending on the hardware, of course. So you wouldn't want to use a laptop that provides you half the performance that it can give you. So for this reason, Intel and AMD provided hardware level AES instructions on their CPUs. And if I'm not mistaken, some ARM processors also planning to have these instructions. So they are really fast. And a good thing is that you can also use these AES instructions to generate random numbers. For instance, Intel has a property that uses this AES instructions to generate random numbers. Since this is at the hardware level, you can generate random numbers in a really fast way. And this is really important because when performing some experiments on your on software, you might need random numbers a lot. So this is the best way to obtain really random numbers, because they perform AES encryption and provide you actually the ciphertext. And as you might guess, through this lecture, you would realize that the ciphertext actually looks random if your algorithm is good. So for this reason, whenever you need a random number, you can use this AES instructions. You can also use this AES instructions for encryption, but since this is at the hardware level, we don't know if there's a backdoor in it or not. So when it is up to you to use it. So enter at your own risk, let's say.